Hello, everybody. Welcome to today's webinar, Metal Building Design in RISA. My name is Debbie Penko, and we'll be spending the next hour here discussing metal building design. Starting out, kind of jump in a little bit and talk about this is just a couple images I found of what we're looking at, type of metal building design. So we're talking about it being a pre-engineered structure with cold form steel bracing and tapered wide flange. You've got all sorts of different hot rolled materials in this type of building. The reason I picked this topic was we get asked this often of how to do this type of design. And it's got a couple different things that'll make it a different type of model. And some things that you might want to consider when you're doing this different metal building design inside of RISA. Some of the things to think about while you're doing that type of modeling is it is a multi-material model. So we're going to be talking about hot rolled steel. We're going to be talking about cold form steel. We're going to be talking about the fact that we have cables in there we're going to use cables for braces. Tapered wide flanges design is going to be a little bit different. So if you're used to using RISA with wide flange, we'll be jumping into the tapered wide flange section, which is going to be a little bit more customized. And then bracing. So adding bracing into your model can be something that can have people have problems with. Cable braces in particular, purlins and girts, those types of braces. Lots of questions come up when we talk about how to put those inside of a model and how to represent them. The other thing is connections. So we will be able to take this model over to RISA Connection to do some of the connection design for the hot rolled sections of our model, as well as we can add a foundation to the base of the model. So we've got a lot to cover and model, and what I'd like to do is just jump right in to modeling the structure. So we're going to take a look. We're going to model something that looks very similar to this structure right here. And we'll talk about adding the loads and all the different considerations as we continue to model. So what I'd like to do is just start out by jumping into a DXF. I just drew a frame. I tried to just model here the wide flange, the tapered wide flange frame, the rigid frame that I'm going to be using. I wanted to also put in some of the columns in for those end walls. All the girts and things we can work on along the way, and the purlins, those are things we can add in. But what's nice about this and what gets kind of difficult, and lots of times you kind of think about how you're modeling this, is that the outer edge of that structure is going to be vertical, completely vertical. So when you're looking at that tapered wide flange, you can see that outer edge is completely vertical, and then we taper it inward. So in RISA, we're modeling the center line. So I have a center line dimension here. I just call this a layer center line just for convenience, and I just did a different color to designate that that was the center line. But what I'm seeing here is I actually am going to be slanting those columns inward a little bit based on that center line. So one of the things I really like to do here in RISA 3D is import a DXF. So I can just get started by drawing on this DXF right inside of RISA. So let's do that. I'm going to jump over to RISA 3D. And I'm just starting a brand new model in RISA 3D. And when you start a brand new model in RISA 3D, you have the ability to set a grid. And that grid is just a standard grid that we use. You can toggle it on and off. And instead of using that standard grid, which is just we look at here, it's 30 increments at 1 in each direction, we're going to jump over to the imported DXF. So I saved that drawing out as a DXF prior to starting this model here. And I can then go ahead and find a location for that. We'll leave it at 0, 0, 0. And the plane, I'm going to leave it in as the XY plane. That's the default. It asks me if I need to scale it, if there's what the inches, the units are. And we'll leave everything as the default settings right now. And that's basically, I worked off of in AutoCAD inches. So everything should be fine importing right in. You browse for that file. I actually have my file listed here as my last file I imported. And I'm going to grab it. And I can tell the program here that I want to select all the layers, or I can choose from different layers. If I choose all of the different layers, I can even change the coloring to match there. So I can actually change that color to be green and then say, check all of these and then done. And it pops up and it opens it so that it actually looks exactly like my DXF. Now, this is not a model. I didn't import the model. If you have ever used the import DXF function, that's in your file import DXF, and that actually brings the members across. But in this one, what I like to do is I wanted to actually just be able to draw directly on top of this, because this wasn't the actual model. I wanted it just a representation of that. So what I'll start by doing here is I'm going to create, so actually I want to show you guys that that is just a grid kind of behind there. We'll pop back into the XY. Now, what I'm going to do is create section sets. This is a perfect model for section sets because it helps us to define a group of members. So I can tell the program here I want all of the end wall columns to be the same member, all of the end wall beams to be the same type of member. The rigid, we'll do a rigid frame column, let's see, and then we'll do a rigid frame beam. So you can enter in all those shapes. And we'll just start out here by a shape for the end wall column. We're going to just use tubes just to kind of mix it up a little. We will be using, let's say I'll pick out, and the database here, if you open it up, you'll have square tubes at the top of the list. And I want a square tube. I'm going to just use maybe a 10 by 10, let's say a 6. And that 6 there, that indicates that that's going to be let's see here, 6 is going to show you right in the wall thickness. It's going to be 0.349. So you can always check what your thicknesses are right there. I'm going to say OK. And then at the type, I'm going to call it a column. The design list, I'm going to say that it's going to be a square tube. I'm going to use this material type called A1085. And that's a newer material type here we have in the program. I'm going to match it with the material type A1085. The other thing I'm going to use is the end wall beams. So those end wall beams, they can just be a standard wide flange so I can just pick a wide flange shape here. Maybe I'll just pick a 12 by something and we'll see if that works. And this is just a starting point. So we can always size that to something different. It'll be a wide flange and we'll call that A992. Now the interesting ones that come along. So I could use the same member for the rigid flange, for the rigid frame column and the rigid frame beam. But what I'm going to do is maybe I want to size them differently. So I can just sort of enter them in separately as 2 different line items, and then I can size them up individually. So these are going to be the tapered wide flange. So I'll jump into the shape selection tool, and I have wide flange, but the tapered is what I really want. And I have a list of ones that I've created in the past. What I want to do is I'm going to add a new one. And when you open up the tapered wide flange database here, you have the ability to enter in anything you want. I'm going to call this the metal building column. Metal build call, we'll call it that. And then the depth and anything can vary. So you can vary from the start to the end, the thicknesses, whatever you need to vary, you can have it vary. And I'm just going to set up some parameters here. I'm actually going to vary just the actual depth is going to change. So it's going to be 24 to 40. That's the only thing I'm going to change, but I'm going to keep everything else the same. So I'm going to say here that this is going to be a 12-inch. And we'll call this all 1/2 inch. And we're just going to take a first pass at this design, see if it works. And then we can always go ahead and size these up as needed. So I'm going to go ahead and go, let's see, we'll call this 1/2 inch and we'll use 12 inches as our flange width there. So everything is going to be a 1/2 inch. Now you can then, if we just said everything, you see it pops to the bottom, and I can pick that metal building column, and I'll say, that question is asking me, do I want to save this permanently to my database? So later on, I can come and use the same thing. I'll say, sure, we'll save it to my database. Otherwise, we can save it just to the model. So I'm going to go ahead and say that's a column, a wide flange, and an A992. Now, I could say the same thing, metal building column, or I can enter it in separately. And as I mentioned, if you are going to say that it's going to be the exact same design for both the column and the beam, and you don't want to size them up differently, then you may want to go ahead and do them at the same exact shape type. But if you do later on want to do that and change them separately, you can name them separately. So we'll call this one metal build beam. And I can use the exact same parameters, or I could change them right now if that was something we needed to do. But I'm going to go ahead and just use the same parameters, and we'll start off with this. So we'll say 12.5, and then we're going to use that 40 inch. So I've got a And one of the things that's interesting to note here is there's a start and an end. You could flip-flop it. Of course, that would just, the only difference is you'll make sure when you're drawing your member, the start is where you want it to be versus the end. So I'm going to say okay. And I'm going to see that I have it there at the beam, and I can say okay, and I will also make that permanent to my database. And I will change this to A992. So once I have those in place, all of my hot rolled members are in place, I also want to consider my bracing. So I'm going to go ahead and create some cold form. I'll create the girt member and a purlin, and we'll call those, I'll jump in here and we'll call this shape. We can see we have a variety of different types of shapes for cold form. We're going to use the Z shape here with the lips. So I'll go ahead and that girt, I'm going to use something maybe like an 8-inch. And we'll pick out an 8-inch here, something reasonable, and say that that's okay. And then we'll go ahead and pick out maybe a little bit larger for my purlin, again, a Z shape, but this time maybe we'll do something like a 10-inch, and we'll pick it also here, the same thickness. The beam type is fine. We can keep it called a beam type. The design list is important. So if the program is going to be giving us suggestions for this type of shape, we want to make sure that the program knows what type shape to give us suggestions for. So the ZS will have to pick that design list in order to tell the program that. And I'm going to leave all of that, the material as it is. So I'm going to close that out. I've got all my section sets laid out. So that allows me to just start drawing my members without consideration now of the member shapes. I have them already programmed in. So I can draw new members, and I jump in here and I can see, instead of just assigning a shape directly, I'm going to pick from assign a section set. And I'm going to start by drawing in those rigid frame columns. So I'll click on rigid frame column and I'm going to say it's fully fixed. And then I'm going to go ahead and say apply. And I can just click to that grid I have in place. Now, the best thing to do when you're drawing in tapered is to go ahead and draw it in rendered, because you might by accident be drawing it the wrong way. Again, it's just a 50-50 chance that you're drawing it in the wrong way. So it's not the end of the world, but it is helpful to draw it in rendered. And then you can take a look at as you draw it, whether you're drawing it improperly. So I'm going to go ahead and say rigid frame column, and then I say rigid frame beam, draw the same thing in. And now, since I knew that the shorter end is up here, I need to go ahead and draw it from that point and from the top ridge and draw it back down to the columns. And then I can go ahead and look at that in isometric view and then confirm that I drew that in properly. So once you have your one rigid frame in place, we can do is go ahead and copy it. So I'm going to use the copy command, and I'm going to go and click on that copy. Now, it's always good to reference which way you're going. Is you'll just look at the global axis in the upper left corner. So we want to copy this in the Z direction. So we're going to go ahead and copy this at 4 at 15 increments. That means I'm doing 4 times at 15 feet. The increments here listed above in the units, it says feet. So I just push apply, and I see that the frame got copied by that many times. So I've got my basic rigid frame in place, but I want to put some of my end walls in. So the way I can do that is I can unselect everything, and I'm just going to rotate this a little bit, and I'm going to select just the one frame I want to copy. And I'm going to copy it in the Z direction. I'm going to copy that one more time, but only by 15 feet. So I'm going to say Z direction 15, and I copied it out that way. So this is going to turn into be my end wall. So I'm going to go ahead and unselect that one, and I'm now just looking at that one frame. Now, the other piece here, though, is my grid is back here, my drawing grid, which has all those nice columns lined out for me at the end of my structure. I want to drop that grid back over in the right location. So if I hover over this node on the bottom right corner of my screen where my mouse is over here, you can see it says 75 feet. So I can change the grid location. I'm just going to click back on that grid. I'm going to say, instead of being here in the Z direction of 0, move over to 75 feet. Now, to reload this, all you have to do is just pick it back up, and then it's like redrawing it right back in. And now it's in place over here. So we'll go back to, and one of the nice things too is to lock your model. It's really easy when you're drawing in 3 dimensions to grab the wrong thing. So what I do is I click on this lock button, and it locks out everything. So now we'll go look in the XY view, and I'm looking at this frame straight on, and I can draw in those columns. Now at this point, maybe we don't want to look at it rendered, but we are going to shift here. I'm going to change these beams. Instead of being the properties here, they're going to be, instead of the rigid frame, we're going to take them to be the end wall beams there, and we'll see them change. So I'll go ahead and just change those, and it's really easy to manually double click on a member and change its properties. And then I'll say okay. And then I'm going to switch out of that rendered view and just look back at everything as a centerline element and start drawing my columns. So I'll go to end wall column, and I'll go ahead and zoom in a little bit here, and I can see I'm zooming right to the member, and I'm going to click on this and click on the member. Now, the reason why I'm allowed to click on that is that I can see that there is actually the grid behind it. So it allows me to click on that. So I've got my end wall in place, and I can look at that in isometric view. I'm going to unlock everything just to get a perspective. And now I'm going to copy this backwards because I want another end wall on the other side. So what I'll do is I'll go ahead and say copy one more time. And I'm going to come in here. I'm just going to say clear, and I'm going to say that I want to copy that back by 90 feet. So I'm going to go in the negative direction. Always, you can see that global. This was the positive direction. The negative direction is away from the capital Z. And I'm going to say negative 90, apply, and that's where it then draws in my end wall. So I've got the ability here now. I can see all of my members are in place for my frames. Now I just need to start worrying about those purlins and tying everything together. What I'm going to do now, though, is I'm going to get rid of that grid, so it's kind of not in the way anymore. And one also thing I'm going to do is I'm going to take the snap options off. It's really easy to click to the wrong point if you have your snap points on. So I'm going to say snap to options, and I'm going to turn those off. Sometimes it's, those are the things that people have problems with modeling. You just sort of quickly slip on the wrong portion of the beam, and then you end up with things out of skew that you didn't realize. So clicking on turning on and off grids and things like that can help you really get around that. So what we'll do here, we're going to go ahead and draw those purlins across the top. To do that, I can go ahead and I'm going to say here, I'm going to split those members. So if we draw members and go to the split members tool, I can see I have a number of equal pieces. I have a member, and I guess I didn't mention the how long this is, but let's take a little measurement of that. It's around 60 feet is what I've got for that member at the top. So what we'll do for splitting that member up, we're going to say that is going to have about 5 foot spacing for our purlins. So we can say number of equal pieces, and for 5 feet into 60, it's going to be about 12 equal pieces. And we're going to say, don't actually split the member, just add joints. All we need to do is have joints along the top. So we're going to say apply that individually, and I'm going to click on these members right here, and that allows me to see that I have clicking points for those purlins. So then I can go ahead and draw those purlins in. So just by going to draw members, I'm going to pick out the purlins, and let's see, oops, we want cold form, and we'll see here the purlins, and I can say apply. So I can just draw those right in across, and what's nice is we see that we have those nodes to click to. Maybe get rid of your node labels so it's easier to see. If you have problems seeing the stuff in the background, I can lock the members and behind there away from view. Here's one that's a little tricky. You can zoom in real tight and see so that purlin's not crooked, and we can then draw this across. So when nodes get really tight like that, it's you can make a decision. Maybe you want to just click it to the column, but it would then be skewed, and not the end of the world, but sometimes that can cause you a little bit of a nightmare if you're trying to copy things down the road. So you might zoom in a little bit and get to the right node that you want. Another approach would have just been to copy that column location instead. Oops. Instead of actually just using so we could, instead of saying equally at 5 foot, maybe do it a little bit more on the columns. That's another approach, and probably a little more, you would do that more in the field where you're going straight there, but sometimes you work in both directions there. So I'm almost finished with this, and what you'll notice is I am drawing these purlins in fixed. And that's an important piece that we can talk about here. So let me zoom out a little bit, and I'm going to unlock this. And what we do want to do is we want to make sure we copy those purlins directly backwards and have purlins everywhere. So what I'll do is I'm going to unselect, I'll lock out everything one more time, unselect everything and just select the purlins. And we're going to unlock this model one more time here. And just for reference so we can see that they copy properly, we're going to go ahead and copy those purlins backwards. And we'll copy them here. We'll say that this is going to be 5 at 15. And we'll say it's going to actually be negative. If you look at that here, we're going negative space. So I can say apply and they copy it back. Okay, so now you have your purlins in place, and I'm going to lock this out one more time before we're just looking at the purlins. So one of the things that those purlins is to think about is that how are you going to actually connect those purlins? Are they continuous? Are you lapping them in a way that you can say that they're going to be a continuous member? So it looks like people do this a variety of different ways, but probably you can consider them to be continuous. What that does mean, though, is that are they really continuous when they connect to these back frame? Maybe they're continuous along their length of the member, but maybe not back when you get back to this column and this last frame. So what might be good is to just to lock everything and have it pinned at these back frames here. So what I'll do, I can modify those members. I can say, I'm going to go ahead and unselect everything, just select those members at the end. And we know that we drew this from left to right because that's how I was drawing it. So this is the start portion of my members. So what I can go ahead and do is just modify the properties and say that I'm going to do a release there, a bending moment release on the start release, and keep the fully fixed on the end release. And just those members that are selected right now, we'll go ahead and say that those are going to be, for all of those members, we're going to release that side. And then that works on just one side. And if I unselect, I can just select everything so you can see that. I'm going to unselect everything one more time, select the back side of the structure, and we'll go ahead and flip-flop that. So instead of saying the start end release, we're going to say that's fully fixed on that side and bending moment release on the end release, and then say apply, and you get that pinned on that side. So now when we look at all of the members here, they are continuous along their length, connected to each other continuously. So the moment's going to be distributed along that member as a continuous member, but then as it connects back to the last frame, it's going to be a pin. Okay, so you can do it that way, but again, you have to think about how your members are connecting in order to see how that works for you. I can unlock the whole structure, and then we can look here at this member, this purlin directly. One more thing to think about with these purlins, and let's go ahead and look at the structure kind of dead on again, is we can look at how this structure, how those purlins are looking on our screen. I'm going to go ahead and change the transparency of this member so we can just kind of see through it. It's a helpful thing. Inside of the members plot options, you can see it rendered, and you can change the length of the render. You also can change the transparency. So I'm going to say that, and we'll go a little bit less on that transparency so you can see. So basically, those purlins are Z shapes, but they're oriented straight or vertical. And that's probably not how they're going to be built. Now, this is not a very big skew, so it may not really make that much a difference for our model. But if you have a high pitch, that member orientation does make a difference. This is cold form that we're talking about. So those lips orientation is a big deal in how they actually, how they develop the forces. So if we go back to my show here for a second, let me just think about how that works. So all we have to do is just figure out that we can rotate them, and we just rotate them based on the rise and the run. So if we're talking about 60 feet and we're looking at a 1 on 12 or a 5 foot rise on that, all we have to do is use the tangent to find that we have a 4.76 degree rotation on those purlins. So what we'll do is jump back into RISA 3D. And I'm going to go ahead and unselect everything in my model and just select those purlins. Now, probably the last one will be straight here, so I'll leave that one. And I'm going to just kind of use my mouse and select just the ones that I want to rotate. So I'll leave the one at the top of the column. I'll leave the one on the top of the pitch, and just these here along that distance. I'm going to go ahead and go into the modify properties one more time. And that modify properties, all I need to do is use the rotate button. But by the way, don't forget you had some of these other modified properties going on here. This is a common mistake where you go in here and you forgot you just did that. It's a really useful tool that RISA does where it remembers the last thing you did, except when you don't want it to. So what we'll do is we'll say clear use, and then I'm going to just say just use the rotation. So go ahead and say 4.76. Now, sometimes I mess this up. Sometimes I want it to be a negative and a positive. I actually think this is going to be a negative for this direction. Not a worry. If you make a mistake, you can always push undo. But I'm going to say negative 4.76. I think that will be the one. Yep. And it did look like it went to the right rotation. So we rotated those slightly. Now the other side we can do just as easy, just unselect the entire model. And since we're over here, we just zoom in on that side and we can just highlight the top members right there. Okay, and then we also just click on the modify properties, and here we'll just say it'll be 4.76. And it remembered the last thing we did, so we just say apply, and that then rotated it slightly on that side. So pretty easy to draw in those purlins and rotate them. Let's look at this model again back in isometric view, fully view, look at everything on the screen, and we then see all of our purlins are oriented properly. Before we forget, let's go ahead and put some boundary conditions on the model. So I'm going to go ahead and say modify boundary conditions, and I'm just going to use a fixed boundary condition. I'm going to say apply and highlight the whole bottom of my structure, and I then put a boundary condition along the entire structure. Okay, now the last piece here, we've got some girts that we have to worry about. So we want to worry about those girts all along the outside of the structure. I'm going to go ahead and I'm going to get out of render because it's a little complex to see. And we can do is just pick out the columns to worry about. That's all we're concerned with at this point, is drawing those girts along the columns. So what I'll do is I'll unselect the entire structure, and I'll use the selection based on criteria button. If you click on that, that'll help you guide you through what you want to select on the screen. So we want to select only members, and we want to select the columns. So I'll go ahead and I'll look at member type, and I see column listed here, and I tell the program only pick up my columns, apply, and I can say, okay, now everything else is kind of out of view or unselected. But to really get that away, let's lock it, and then we can just see what we're looking at. We can then possibly here, so what we want to do is we want to make sure we can see, split these members, these columns along the distance to so we can draw those girts in. So what we'll do is we'll go ahead and go to split members. It's under the draw member toolbar. You can click on split members. We just went in and split it 12 pieces. Now we're going to split in an actual location. So typically here we're going to say that that's going to start maybe at 7.25 feet or 7.33 feet here. So we'll say we'll put that specific location. We're going to just add a joint along those columns here at 7 and a little bit change feet here, say apply, and oops, I actually want to do it to apply all selected members, and every single one of them happens to get a node there. We'll also do the same thing and at one more level, maybe at 12.33. Now, one of the important pieces that I did, because I knew what I was modeling, it was important, was that I used the I and the J ends. I drew my columns from top to bottom, or actually from bottom to top is how I do it. So that's an important note. And sometimes you just kind of willy-nilly draw columns in and beams, but it is important to go in the same direction because you can use tools like the split member in a fast, easy way. Had all my members been going in different directions, that wouldn't have been so easy. We would have seen that some of the nodes would have popped in the wrong direction. So it's always a good thing to sort of consistently draw your members in how you want to draw them, so that you can always be from one same direction, I guess. It doesn't matter from top to bottom, but keep it in the same direction. So the other piece here I'm going to start drawing in is the girts, and I want to make sure that those are going to be pinned. Girts are interesting. So if you want to draw those girts in, I really don't think I'd ever draw in a girt as a fully fixed. I think it would have to be a pinned, whether it be flush or bypass type of girt. You have to really think that how would you get that to be a continuous member, unless you're really lapping it like you would lap the purlins. Now, again, that's something you might be doing. If you are, then you might be considering it fully fixed. But I would say probably the way I'm seeing anyone building these, that you would be a pinned for that girt. So you'll go ahead and draw that all the way across the structure individually as segments because they are pinned. So we're not going to be transferring any of the moment into those girts. They're just going to be there to help support the sheathing and apply some of the loadings there to it as well. So one thing I didn't do is I didn't think about the rotation about these girts just yet. So what you can easily do that and go ahead and make that modification. So I'm going to go ahead and let's give ourselves a little doorway here. We'll take off these girts here, and we'll go ahead and say, now we're going to worry about those girts rotation. As we zoom in here, probably not the way we want to have those girts oriented. So what we'll do again, we'll use that unselect tool and we'll just select those girts, clicking on the select based on criteria, and we'll say, hey, clear selection criteria. We want to just pick out the girts and say okay, and then they are now selected. The modifications we want to do to them, let's go ahead and say modify their properties. What do we want to do? We want to make sure that let's clear the use first, and we're going to say 90 degrees, rotate them, and then let's also call them V braces. Now, or H braces, each one. Actually, let's call it H brace. And the reason why I'm calling it an H brace is when we start to apply loads to these, the girts probably aren't going to be seeing that load maybe. We'll see the difference about how that'll work. It's up to you whether you do it one way versus the other. But again, if this is to help support the sheathing, maybe they would see the load, maybe they wouldn't, depends on how you're attaching that. So I'll see how the top are actually the purlins are going to see the load of the area loads and the girts won't, and we'll see how that worked because it was based on the material type, or the member type, excuse me. So I zoom in a little bit here. I have most of my structures all set to go. We have our purlins in place, we have our girts. The next piece we needed to worry about was those cable cross bracings. So let's go ahead and go back into the wireframe view, and we'll look at when we add a cable, the things we need to consider. We can draw in just a cable member or a solid round, but it's really important to add a material type called cable, or called whatever you'd like to call it. But the piece that we're going to do when we add this cable element is we're going to drop its density down to 0. Why that's important is when you add self-weight to that, what's going to happen is if you were applying self-weight, you'd see that then you'd get some loads on that cable element and deflections that wouldn't be realistic as you start to apply the loads there. So they'll start to become a problem, and they won't behave really like cable elements unless they enter in a 0 density. So we'll start with a cable element with a 0 density, and then we will start drawing. We can just draw those cable members directly into our structure using assign the shape directly. It's going to be a hot roll to assign the shape directly, and we can say we're going to use a solid round bar. I have a couple bars available. We'll use the 3/8 inch cable. You can add a cable element in there. You'll just see I just have one already built in place here. So I can go ahead and draw this 3/8 inch cable directly into my member. It's going to be pinned at both ends. It's going to be let's call this one a V brace. And we'll say here, if you wanted to pick what type of suggested shape, we will call it bar, and A36 is fine. Now, the other thing you can do to it is call it a tension only member. Now, that's a pretty important thing to note, is this isn't to be, really a cable is truly a tension only. It cannot take compression at all. That's one of the few elements that you really can say that it is tension only. And that's important to note, that sometimes people use that as other member says, and you can try that, but a cable really is the only true tension only member. So I'm just selecting this one bay. I'm gonna lock out the rest of the structure. I'm gonna start drawing in this cable element. So it's pretty easy. Just sort of find your cable element, just draw it, and I'm gonna say it's gonna go every 4 bays. So we'll just sort of scran around here and draw in every 4 bays. And that should hit us there. Let's see, 1, 2, 3, 4. And I'm just going to go around the whole structure and draw these in. So we go 1, 2, 3, 4. Oops, I don't know if that was 4 quite. Let's go ahead and say 1, 2, 3, 4, and finishes there. And then you can just zigzag the opposite direction. Pretty easy to draw these cable elements in. And when you finish that, what you can do is, again, unselect everything, just pick up those cable elements. So finding on this list just the 3/8 inch 3/8 cable, say select only those. I do like to unlock everything. You don't need to unlock everything, but just helps me guide myself, make sure that I got this correctly so when I do the copy. So I click on the copy, and I'm just going to say clear and copy this down by a couple bays. So a couple bays means about -30 feet. Each bay is about 15. So I can say apply, and I've got a second row of framing in there or cable elements for me. So now I've got some lateral resistance when we start to blow on this using my tension only members. So then the next piece here is going to be apply the loading to the structure. So when we go into the loading, I'm going to go ahead and go into the basic load cases. I'm going to call this a dead load and a live load. And the load that I'm going to do is the wind load in the X direction and the wind load in the Z direction. Notice I just skipped a space, just helps me to separate things. You can add notes in there. You don't need to, write on every single line in the basic load cases spreadsheet. Now, when I do pick up the category, I want to make sure not to use just wind load in each one. It's a directional load, so I need to make sure I separate them. Wind load in the X direction, so I'll find that one here, and wind load in the Z direction. As I scroll down, I find wind load in the Z direction. Self-weight's an easy one to do. I can just say a -1, dead load, and I'm set to go. Now, the best thing I like to do is I like to, before I even start applying loads, I always go ahead and just test the model. Does this make sense? Did I make any modeling errors? Hopefully I didn't, but let's check. And what I like to do is just create a load combination called test, and I just give it maybe just the dead load with a factor of 1. Now, that means that all I have in this model so far is self-weight. In the Y direction, that's what this Y -1 in the gravity direction does. And I give it a dead load. Here I'm calling up that category, and I'm just applying that one load case. I solve this load combination, and I cross my fingers that I didn't make any modeling errors. And this note tells me I have no P delta, I didn't use P delta, which is okay for this stage of the model. It does say I have an instability, so I have to zoom in there and just see what's going on. It looks like I missed that there, right there. So that's important. I have just a small little instability, not a big deal. What I can do is I can try to fix that. Either by, we can just reassign it. Let's just reassign that one. So this now purlin goes to 290 instead of going over to the 302. So we'll say it goes to 290 and it will break the solution and it pops it over there. Now, hopefully that's my only problem. It looks like I have a couple that are not quite attached there. So I might have a kind of a issue with these purlins that it looks like I just had a small modeling error as I go around. So you can sort of zoom in a little bit, but you know how I detected that? The best way to detect that is really to just run that test combination and make sure you see that. So it'll tell you whether you have an error. Also to test, hey, did things work out well? Looks like I have some problems in my framing. So the best way to do that, to look at that, is to say, hey, I got to look around and check that I have some things that are not quite attached. So you can kind of zoom in a little bit and look at the deflected shape and see what's going on with those members. So you can kind of take a look at the different things that you have and all the different properties. And it looks like my cable elements, as I mentioned, I didn't use my cable elements there as my properly. So I have a couple of cleanup things to do in my model. So we'll go ahead and let's just sort that out a little bit. So I'm going to do a sort on this member, and it looks like in my cable element, I forgot to use that cable material I used. And so I sort of proved the point that if you do not use that cable element material, you'll have a problem with that because it has density to it. So I'm going to go ahead and switch that. Okay, the next step I'm going to do is I'm going to go ahead and go into the load combinations, add the loads I applied to the structure. So I'll go and I'll say here, I'm going to use my area load. I'm going to apply it in the A to B direction. And I'm going to say I'm going to use maybe a -0.01, which is about 10 pounds per square foot. Now, A to B direction is important because it's telling the program how to load it. So it's going to load it from the click, first A click, and then the second click is a B click, and that's the direction of the loading. So I'm going to click on the first click is over here in the corner, and my second click is over at the top of the pitch of the structure. And that will give me the ability to see that I'm going to click around the structure, and the A to B, that's the arrow pointing in those directions. So what I'm loading is the purlins. I can do that and the same thing over here. And then it will see that the arrow goes in that direction. And so you see that instead of loading the actual rigid frames, we're loading the purlins, will then distribute to the frames. So you've got the ability here to apply the loads in either direction. And it's important just to always look at the actual arrow, making sure you do that properly. Then you can go into your basic load cases spreadsheet, and you can see that there's a little 2 there. I can go ahead and I can copy that so I don't have to draw it again from the dead load into the live load. And I'm going to go ahead and copy it directly into that live load. And I see that I've got the 2 listed there for us. And then I'm going to go ahead and go into my, so I have open that up and clicking on that gray 2 gives me the ability. Now, instead of using that 10 pounds per square foot, I'm just going to say the live load is going to be 20 pounds. So I can just override it in the spreadsheet. It's pretty quick and easy to do. The next piece I'm going to do is apply the wind load. So I'm going to apply the wind load in the X direction. Now the wind load in the X direction, we can see here it's got the load in the X is going to be in and out of the page. I can apply that wind load directly to the structure. I'm going to choose this to be wind load in the X direction. And I'm just going to do a back of the envelope, say, let's say 20 pounds per square foot in the one direction from A to B, and that needs to be in the X direction. And then I can apply that here right to my building. So if I apply that, actually I apply it to A to B, I want to click on the direction. It's important for me to, the first click is over there, and I see that the arrow goes this way. Now this is not an open structure, this is going to be an enclosed structure. So I'm just applying a standard area load. The tributary area of that is each column is going to be calculated and applied at solution. Then I'm also going to apply a suction load at the other side of it, maybe just a 10 pounds per square foot. And I'll go ahead and draw in that. Of course, again, thinking about the direction, which is important. The A to B click is really important for you to click that properly. And you can see the arrow there. The other one, that last load on the Z direction, we'll go ahead and go to the WLZ, change the load direction. And we're going to start with the 20 pounds, and we'll start over here and draw that across there. And then I'm going to go ahead and do that on the other side. Instead of 20 pounds, we'll call that 10 pounds. So I draw that across there. And I then see that I've got 10 pounds in each side, and 10 pounds on this side is suction, and then I've got 20 pounds on the other side. So once I've got all that in place, I'm going to go ahead and I can go to load combinations. And this time for real, I can apply some real load combinations. So using my load combination generator, I can go into the load combination here, and I'm going to say that the load combination is going to be the 2012 IBC ASD. I didn't apply any specific RLL or SL or snow load or rain load, but I do just need some standard gravity loads. So I'm going to say generate, and I see that the gravity loads are there in place. Then I'm going to go ahead and say the wind loads, which if I click on the wind load here, I'm going to use the X and the Z. Because I use WLX and WLZ, I use the X and the Z there, and I can say generate and then close that down, and I see that it called out all the wind load combinations I needed for the WLX and the WLZ. And then I can then start to just solve the model. So I'm going to solve with the batch. I'm going to run through the design. And I'm going to see here that it's going to go through all the different load combinations. I ran the solve the batch with the envelope. This is something that went into version 12 here. It allows you to solve all individual combinations as well as finding the batch the envelope solution. So what we call a batch, when it goes through each individual combination, and then it envelopes it for you too. So you get 2 sets of results, which is helpful, especially when you're looking at design. So it's nice to see that. So it takes just a couple more seconds here. We're looking at load combination 10. It's going through. It just gives me a warning I didn't use P delta just yet, and that's okay. What we want to see now, first I want to see here is some of my loading. So the loading got applied to the structure based on what we show here is called transient loads. This is really important if you want to verify what got applied to your structure based on the area loads. So we see that transient area load 1 is going to be giving us that dead load combination, and that's what we see here got applied. So when we said to the program we use an area load, it applied it as a transient area load. And that turned it into these distributed loads on each individual member. And then we can see that happened also for the live load. And then we look at now the wind loads, and we see that the wind loads got applied to each of these different columns. And then we scroll down and we see that on the Z direction, we got them also. So what was happening is it's calculating that based on the tributary area. So you've got your load combinations all in place. You can see that we can look at the loads, and then the big important piece here is our design results. So we can open up, and the first click you click on that design results, this is the envelope results, which is important to us. We can click on the code check information and sort it. And we see we've got a long list of some overstressed elements. So when we look at these metal building beam element that we have in place here, what's important to note is it looks like they're highly stressed. But what we forgot to really address before we went ahead and checked the design is that we did not tell the program anything about the bracing. So we can go and look at the member here, and each individual member is considered itself full span without any bracing. So if we jump over into the members here spreadsheet and we scroll up to the top, what we're worried about here is these rigid frame beams, and we go to the hot rolled tab. We have some information listed in here called LBYY, LBZZ, LComp top, LComp bottom. And what these are going to give us here, if we look at the bottom, if you ever forget what's going on in here, it's telling us here unbraced top flange length, and then we see here unbraced length of, for local YY bending. And so in our model, what we've got in there is that we have at least the LComp top is going to be braced at every portion that we have the purlins running over. So we can go ahead and we can highlight just the LComp top portion at least. And we can say, hey, all of those beams there are going to be fully braced in the LBYY every 5 feet. So we'll go ahead and say that those are braced at 5 feet. If we really wanted to go beyond that, we might be able to say that the LComp bottom, maybe we need some bridging. Maybe we're going to be able to say that the LComp bottom is going to be braced by bridging, L torque, LBYY. These are things that we can say, hey, let's take a look. And one of the things you can do also is think about, if you put your local axis on and think about what's going on, let's unselect the whole model and just look at maybe just one of these members. So we're talking about the bending about the y-axis. Bending about the z is not going to help you much. Nothing's really there, but about the yy, maybe that'll help you if you put some bridging in. So let's go ahead and tell the program, hey, let's change this to 10 feet on center, that we're going to have some bracing in both the bottom, LComp bottom. We'll also say that bridging is going to help us with the L torque as well. And then we'll rerun the model and see if that helps us in any way. So that should, as we run the load combinations, really change some of the reactions, and we'll see more of the design. Analysis didn't change in any way, but what did change is that the code is now going to change its unbraced length instead of using the full distance. By default, it's conservative for the program to say, I don't know what's going on with the construction of this, so we're using the full length of the member. And then it's the engineer's discretion to say, well, actually, this is bracing this. Now, it is important to also make those considerations. Sometimes things aren't bracing, even though you might say, hey, I have something framing into it, it's bracing. But what if it's a very large member and you're not going to consider it a brace point? So that is something to consider too. You have to be realistic of what can brace what. So all of a sudden, things look a lot better. So it's kind of a false positive there when you start looking at design results and you haven't even thought about unbraced lengths. So those seem to be really good. You can look at our cold form steel, and we haven't addressed anything with the cold form steels. What we would want to do, and I'm going to kind of fast forward past that a little bit because I do want to jump into connections too. But what you would do is you could tell the program LBYY. If I zoom in a little bit, LBYY would be maybe fully sheathed. If you can tell the program that it's being sheathed, you would say it would be 0. So the members going back to cold form, and you would say the LBYY for all of the girts would be at 0 for the LBYY. 0 means fully braced. And then since LComp top follows LBYY, you can see it just matches whatever's LBYY. So then we would only need to enter it in for the LBYY. So I'll go ahead and do that. I do want to jump forward quickly here. So we'll say yes, and we'll say 0 in there. Okay, before we move past that though, I do want to add some connection rules. So we're going to jump into the connection rules. And in RISA 3D, we do all the design of the structure, but we have a program called RISA Connection, in where we can design the connections of the members for hot rolled. So in here, I might use an end plate connecting those tapered wide flanges into the columns. So what I can do is I can go ahead and I'm going to unselect everything and just select the members. We'll clear the selection set and we'll say, hey, just pick out those rigid frame beams. Okay, so just those. We'll pick out the end ones as well, and just as easy to click on those there. Now I'm going to go ahead and turn the local access display off so that it goes away there. But what I do want to see is the connection rule. So you can assign the connection rules to the program just at the ends there by either double clicking on a member and looking at that member's end releases. So this would be probably the end release. We can call it a end plate moment right there. Oops, and that is actually the wrong side. It's going to be the J end. So we'll use this one as none and the end plate moment. So you'll see that it names the side there. We're going to say that this side is going to be the J end. And so I can do that either by clicking on it, double clicking on it and changing it, or I can go to modify properties and we'll call this the J end, and we'll change that to be the end plate moment and apply it to individually. And I'm just going to click on those, and you see click, click, click. It allows me to go ahead and click around the structure. And the other thing I can do is on the other side, let's double click on that side, and we can see that this is probably our I end, but we will double check here, and it's the J end actually again. So we've actually easy enough. We can just say J end on that side, and we can actually do it to all the selected members, and that would then go there. So now if we look back at our structure, we can solve the model one more time, and I'm going to solve the envelope with the batch, and I can then take it into RISA connection. So once you've gone through all of this, RISA connection is going to use all of the load combinations that we have, and it's going to take every single element, all those elements we defined just now, and those are ones going to be brought into RISA connection with all the load combinations and the governing load combinations too. So we'll know which ones are the worst case, and we'll be able to design those end plates right inside of RISA connection. Your model gets saved here in RISA 3D, so it is one model, and then we have a separate file for RISA connection, and it tells me don't worry about the P delta for now, that's okay. And we'll jump over in using the director button at the top, we'll say let's open up RISA connection. So it tells me, well, we've got some problems with those members. Let me jump in here. I'm gonna go ahead and say it looks like we got one member that we can't quite see, so we'll go ahead and just go ahead into this one and run it. Let's see. So let me run the batch here on this guy. Oh, sorry about that. Let's run the batch solution and solve that. And we'll jump right back into it. It looks like we had a little problem with our end release, our member types. Let me make sure we get those member types properly. So RISA connection member information also is listed right here in the member spreadsheet. So you'll notice if you wanted to, I was doing things graphically. You can do it by double clicking on a member. You can go into RISA connection member spreadsheet and it'll go right back into that. So let me close down RISA connection for us and we'll open it right back up again. And it runs through all the load combinations we just created, and we'll go ahead and we'll then see it's going to do our end plate connections, and we'll say RISA connection. Right, go ahead, design connections, and we're getting quite in there for a sec. Let's see. We'll try one more time here, and we'll jump in. Looks like it's not quite pulling it up. Let me jump back in here and let's see if we can call this we'll double check. Oh, looks like we lost our end plate connections here. So let me go ahead. We're gonna, I'll show you here RISA connection in a second, but let me go ahead and we can go in just directly into RISA connection and see. So I will create a new file here in RISA connection just so we can just see that. Looks like I lost my connection types, but what I wanted to show you is the ability to go ahead and you can create those end plates right inside. You can either do the actual splice there, or you can do it here as an end plate to a beam column, and then it will allow you to develop that end plate right at the end of that column. When it comes in from RISA 3D, all the loads for us are brought right in, but that loading information is directly dumped right into here in RISA connection. So it'll allow you to design that. And one of the nice parts too is that it runs through all of the different calculations of that connection there for you. So it's checking the bolts, it's checking the welds, but the other piece too is also checking the column strength. So sometimes the governing design check is not only just going to happen from within RISA 3D, but sometimes you'll find that the column strength, the webs, the column yielding there, but web buckling, web crippling, that's going to be actually controlled by the connection as well. So sometimes you don't size up your members in RISA 3D based on the code check in RISA 3D. You also might have to size up your members based on the connection. So that's an important piece that you can do there. So I'm going to also take this model over to RISA Foundation and just show you in RISA Foundation. In RISA Foundation, when you take all of the members across, you've got the ability to see all of the joint reactions come into RISA Foundation, and that allows us to apply footings in RISA Foundation. So I'm going to go ahead and see here, you can click on Assign Footings, and you see the footing there. You can go ahead and define all those footing definitions right inside of RISA Foundation. So for this type of structure, I might just do spread footings, where I can tell the program the type of steel I'm going to be using, whether I want to do equal bar spacings, whether I want to do forced top bars if required. The geometry, the program will size that footing. So go ahead and maybe we can change the footing size to whatever you want. If you want to start at 2 feet, let it grow to 16. Maybe start however variety of size of shapes that you'd like to use. You can say the maximum thickness that you want to do, whether you want it to force it to be square. Each one's going to have a pedestal listed on it, so you can do a X in the Z direction. You can then also see the soil, and you can put some overburdening on those actual footings as well. The program uses a default value for the subgrade modulus and the allowable bearing listed right in the global parameters. So you can just go ahead. It's really fast and easy to put in some footings. I can go ahead and just highlight the entire structure, and each one gets an individual footing. You might put a grade beam to sort of tie this whole thing together, maybe with a depth of 16, maybe a width of 18, whatever type of grade beam you think you'd want there. You can tie it all together using these grade beams. So I just draw from point to point around the perimeter of the structure. And then the program, since you can see the dead loads are displayed right now, but all those end reactions, so for the wind and whatever other types of combinations you created over there in RISA 3D, what gets brought across is the categories. So when you look at those loads here, those point loads, everything is categorized there based on the load categories you use in RISA 3D. So live load, if you use anything, you can see it's all listed here based on those categories. So again, go ahead and solve the model, run the load combinations, and then it sizes those based on the demand of the structure. So it looks like we're really pushing out on those rigid frames, and we're getting some there. We could force them to be square if we wanted to, and you can see that you can sort of look through those footing design. As you scroll down below, it gives you some information. So I am seeing some high level going over unity checks, so we might want to size those a little bit bigger based on the demands that we're getting out of those ones there. If we scroll down, it looks like we're hitting the maximums on some of the edges of those rigid frames, but some of the ones that are working are the small corner ones that aren't seeing as much loading. So it does the concrete bearing check, the overturning check, sliding check. Everything is done there in RISA Foundation for you based on that footing design. Okay, I'm going to go back to RISA 3D, and that is the end of our presentation here. So we'll kind of jump back, and thank you so much for your attendance today.